Welcome back. Today we'll be talking about chi-squared tests and choosing the appropriate statistical test for a particular research situation. We'll begin with talking about chi-squared in general, what it is, and we'll talk about it in the context of an example where we're looking at the distribution of colors of plain M&M candies. We'll also work on running through that same chi-square analysis in JASP and identifying how to write up a chi-square analysis in APA style before wrapping up with a discussion of choosing the right statistical test. And as part of that discussion, we'll go through several different scenarios and identify what test would be appropriate for each scenario given. So here we go with chi-squared test. As you'll see, chi-squared is spelled C-H-I squared. And so that C-H-I is pronounced chi, like a K like kite. Okay? So chi-squared, distribution of color in plain M&M candies. Let's consider that the M&M company is coming out with a July 4th patriotic version of the plain M&Ms. They want the color distribution to be 20% red, 35% white, and 45% blue. To check these proportions, you take a simple random sample of 1,000 pieces and count how many of each color are present in the sample. Strong evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue implies that something may be wrong with the production process. So just to recap, in this scenario, the M&M company wants to put out bags of M&Ms where they have 20% of them are red, 35% of them are white, and 45% of them are blue. We want to see, we can imagine a scenario where, for example, they may have a product control, quality control department, and they want to sample and make sure that the production equipment is running properly, that it is putting out 20% red, 35% white, and 45% blue into these bags of M&Ms. So what they might do is take a random sample of bags and then count out 1,000 pieces and figure out how many of those were red, how many were white, and how many were blue. We then want to test the numbers that we see in our sample against those proportions that we want to see, right? The given population proportions set by the company of 20% red, 35% white, and 45% blue. Okay. So we sample, we get real data, and we want to see, is our real data consistent with that set population proportion, or is it inconsistent, implying something might be wrong? So let's consider some different scenarios. How many pieces of each color would you expect in your sample of 1,000 pieces or 1,000 M&Ms if the true population proportions were in fact 20% red, 35% white, and 45% blue? So keep in mind that when we figure out how many we expect to be red, how many we expect to be white, and how many we expect to be blue, if these are correct, those numbers should then add up to 1,000. Okay, so if we want 20% red of 1,000, 35% white of 1,000, and 45% blue of 1,000. So what we're going to do is we're going to take this number, this sample that we have, multiply it by this proportion, and that'll give us the expected amount that we would expect in 1,000 candies. So to do this, we are going to actually calculate it as 0.2 or 0.20, right, times 1,000. And we can even pull up a calculator. 1,000 times 0.2, and we get 200. So we would expect in a sample of 1,000 candies, if 20% of them are red, then we would expect 200 to be red. Now we would do the same thing for white. 0.35, 35% times 1,000. And this is going to give us 350. And then we'll go ahead and do the same thing for blue. 0.45 times 1,000. And I already know off the top of my head it's going to be 450, but just to show you, here we go. So we would then expect 200 red, 350 white, and 450 blue. And these should add up to 1,000. So 200 plus 350 plus 450. So these are what we would expect if everything is running completely perfectly and we're getting exactly 20% red, 35% white, and 45% blue, and we had a perfect sample. These are the numbers we would expect to see. Now, if you gathered a sample of 1,000 pieces that exactly matched the 3 counts that we calculated in part A, it would not suggest that there's any problems in the manufacturing process, since our actual counts were the same as our expected counts, right? So if we collect our 1,000 pieces and we get exactly 200 red, exactly 350 white, and exactly 450 blue, then this suggests that this does not suggest there's a problem, right? We would say there's no problem here. It's coming out exactly as we would expect. However, due to natural sampling variability, as we've talked about several times in this class, right, that the natural variability that we see when you take different samples, if it's different people, we're going to get different data each time, right? So due to that natural sampling variability, you know that we wouldn't expect the numbers to be exactly the same as what we calculated in part A. They could be off by a few, and it wouldn't be very weird. So let's consider a couple of scenarios. Scenario 1. The company wants to test their production method, and they get 205 red, 340 white, and 455 blue. Just using your best guess from this sample, would you conclude there's something wrong with the production process or not? Okay. So we're up by 5. We have 5 more than we would expect. We have 10 less white than we would expect. And we have 5 more blue than we would expect. Right, so we're up 5 in red and blue and down 10 in white. Do you think that means that there's something wrong with the production process or not? Okay. Well, your answers may vary on this one, but it's not off by very much. So I would say that I would not conclude that there's something wrong here. So personally, I wouldn't conclude something is wrong, right? This is not surprising or weird, right? This is kind of, it's not that different from what we would expect. Now let's consider this scenario, scenario 2. Okay, the company wants to test their production method, and this time they get 100 red, 800 white, and 100 blue. So again, this is comparing to 200, 350, and 450. Is 100, 800, and 100 off enough that you would conclude that there's something wrong with the production process? Again, answers might vary here, but I think in this case, it seems very obvious that these numbers are very, very different from what we would expect. So in this case, since these values are very different to the expected values, then yes, I would conclude there is something wrong, right? These numbers are very surprising, are very weird compared to what we would expect. Now, a third scenario. The company wants to test their production method, and this time they get 225 red, 330 white, and 445 blue. So again, this is in comparison to 200 red and 350 white and 450 blue that we originally said we would expect. So just using your best guess from this sample, would you conclude that there's something wrong with the production process or not? Now this raises the question, how off do we have to be from those expected values to think or conclude that something is wrong with the production process? Now luckily we have a statistical test that helps us to determine whether these frequencies that we see are different enough from the values we would expect if the null hypothesis is true. Okay. So that test is called the chi-square statistic. Chi is the Greek letter, and it looks like a fancy X, and it's pronounced chi as in kite, and written looking like x squared. Okay, so chi-squared. Now, generally speaking, the chi-square statistic relies on the comparison of how different the observed count in a given category is from the count that was expected for that given category. The null hypothesis is that the observed counts are equal to the expected counts. So, in other words, what chi-squared does is it starts out assuming that, everything is fine, that, this is, that there's no difference between our sample and what we would expect. The null hypothesis, as usual, is there's no difference. We then want to actually compare, okay, looking at what we expect down here versus what we actually see up here, we want to compare these, what we actually see with what we would expect to determine, are these differences large enough that we would then conclude, no, that's too weird. We reject the null hypothesis and we say that actually these proportions are in fact different from the ones that we started with, those population proportions. So let's walk through this example, this last scenario where we have 225, 330, and 445, and we'll compare them against our 20%, 35%, and 45% we began with. And we'll use JASP to help us with this process so that we can then determine or draw some conclusion about whether we think something is off with the production process in that particular scenario. Now, the process for calculating chi-squared by hand can be tedious and prone to errors, just as many statistical hand calculations can be. So thankfully, we can also run chi-square tests using JASP, which is much faster and more efficient. Now we're going to look at a data set called chi-squared M&Ms. So let me go ahead and split my screen here. So we can pull up the data file. Now I'm going to go ahead and download my data and open it up in JASP. And you'll see that this data set looks very, very small, right? We have these 3 columns and 3 rows. So it looks very small compared to many of our data sets we've been working with so far this semester. Go ahead and close that and get this where we can see it. Now, in our data set, we can see our variables are color, and this variable tells us the color of the M&M. So whether an M&M was red, white, or blue. 1, we'll go ahead and add these labels in here. So you can, again, open up that menu by clicking on the name of the variable. So 1 is red, 2 is white, and 3 is blue. So we don't have to remember. Now our second column is labeled count. This variable tells us how many of those M&Ms were each of these 3 colors. So in this sample, right, working off of the example that we have 225 were red, 330 were white, and 445 were blue. Now, we theoretically could set up our data differently, where we have one long column that says what color each M&M was. And we would end up having 225 reds, 330 whites, and 445 blues. That is a really cumbersome way to put our data in. And so thankfully, JASP lets us set it up in this way, where it's set up more like a table. Red, we have 225. White, we have 330. And blue, 445. And then our expected values. By setting it up this way in JASP, then we don't have to set it up that longhand way. Now, to run the chi-squared analysis in JASP, we're going to go to our frequencies menu, which we haven't really used yet this semester. So opening up our frequencies menu, under our classical tests, we're going to use the multinomial test. Now we're going to move color, our color variable, to the factor box. Factor, again, just meaning essentially variable, independent variable. And we're going to move count to our, surprise, counts box, right? The number of each one. The number that falls into each of these categories. And then finally, expected counts. How many would we expect if the null hypothesis were true? Now, under additional statistics, select descriptives. And if you want, you can select to look at the plot. And that just gives you that visual here. So we get from our output the results of the actual chi-squared test the multinomial test is what it's called in JASP. You can see that up top, where we have our chi-squared value, our degrees of freedom, and our p-value, indicating significance or not significant. And then we also have, because we selected 4 descriptives, this again shows us our observed values in our sample and the expected values if our null hypothesis were true. And here we can see that distribution. So let's go back and consider our output here. How do we then determine whether we would conclude if there is an issue with the machinery? So as usual, we are going to be examining our p-value and comparing it against our alpha of 0.05. So with chi-squared, if we get a p-value of less than 0.05, then this indicates that our sample counts are significantly different from what we expected, basically under the null hypothesis. So if our p-value is less than that alpha value, then we conclude what we see is significantly different from what we would expect. If our p-value is greater than or above that 0.05 value, then we would conclude that it is not significant. So examining our p-value that we got here, 0.115, this is above 0.05. So in this case, we would conclude that it is not significant. We do not have evidence that there is a significant issue here, right? That these counts are significantly different than what we would expect if everything was running smoothly. So to write that up in APA style, we would indicate, so here's our question that we're answering. So do proportions of M&Ms differ from the expected values of 20% red, 35% white, and 45% blue? Below is the APA style write-up of this analysis answering this question. So let's review the output that we have and then identify where each of the values in our APA write-up are coming from in that output. So we start as usual with a statement that helps to orient the reader, right? What did you do or why are you doing this analysis? This analysis attempted to examine whether this sample was randomly drawn from a population of 20% red, 35% white, and 45% blue candies. A chi-square goodness of fit test, and in the guided notes, we indicate there are kind of 2 different chi-squared tests that we talk about, chi-squared goodness of fit and chi-squared test of independence. In this class, we're just covering this first one. Okay? So a chi-squared goodness of fit test indicated that this sample was not significantly different from this population. Again, not significantly different based on our p-value. And then here we have our write-up. Let's look closely at the style piece here. So we indicated our comparison values in our first statement. We indicated that we did a chi-squared goodness of fit test, that it was not significant, And then here we have our chi-squared symbol. In the parentheses, this is our degrees of freedom. Comma, space, then our sample size, n equals 1,000, telling us how many pieces of candy we had in our sample. Close your parentheses, equals our chi-squared value and our p-value finally. So these ones are coming from here. Our degrees of freedom gets plugged in here. The chi-square value gets plugged in after the equal sign. The p-value is after the comma. And then this n equals 1,000, really that comes from our problem itself, but you can also, again, of course, add these up, and we know that we have 1,000 total. And that's where this is coming from. Okay, so that's our very brief overview of chi-squared goodness of fit test. And next we'll wrap up with looking at how to choose the right statistical test for a given scenario.